Tonight, we're going to talk about the moon and what it would actually take to live there. You've seen the moon your entire life. It's the one place beyond Earth humans have actually walked on, so it feels closer, more familiar, almost manageable compared to somewhere like Mars. But here's what that familiarity hides. Every single mission that's ever landed there lasted, at most, a few days. And even in that short window, the moon still found ways to damage equipment, wear through spacesuits, and put real strain on the human body. Now imagine that same punishment, the same dust, the same radiation, the same wear on the body, but stretched across years instead of days. By the end of tonight, you're going to understand exactly why staying on the moon is a completely different problem than visiting it, and why it would be one of the harshest environments a human body has ever been asked to survive in. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The moon has been with us for as long as humanity has existed. It's the brightest object in our night sky. It controls our tides, influenced our calendars, inspired our art, our mythology, our science. Every single human being who has ever lived on this planet has looked up at that same moon. And for most of human history, it was completely unreachable. A permanent fixture in the sky, present and distant in equal measure, as much a part of the background of human existence as gravity or the wind. Then, on July 20th, 1969, Neil Armstrong stepped off the bottom rung of a ladder and placed his boot on the lunar surface. And over the next 3 years, 11 more men followed. They collected samples, planted flags, drove a small electric buggy across the surface. One of them, Alan Shepard, on Apollo 14, even hit a golf ball that sailed in a long, slow arc in the low lunar gravity. Every single one of them came back, alive and mostly functional. And the world watched and concluded that the moon was conquerable. That's where the story most people tell themselves about the moon usually ends. 12 men, 6 successful landings, one of the greatest engineering achievements in human history. But what that story leaves out is everything the Apollo astronauts couldn't experience, because their missions were designed deliberately and necessarily to be brief. The longest any Apollo crew spent on the lunar surface was about 75 hours, 3 days. They brought almost everything they needed with them from Earth, in careful advance preparation, and they left the moment the mission was complete. They never had to think about where their food would come from next month. They never had to worry about what would happen when a critical piece of equipment broke down with no spare parts. They never had to consider what years in lunar gravity would do to their bones, or what decades of radiation exposure would do to their cells. They never experienced 2 weeks of continuous darkness, with temperatures dropping to the edge of what materials can survive. They never had to manage a medical emergency 238,000 miles from a hospital. Living on the moon is an entirely different proposition from visiting it. Not a mission with a defined end date. A life. And once you start examining what that life would actually look like, once you set aside the inspiring imagery and sit down with the actual physics and biology and engineering, the picture shifts from inspiring to genuinely disturbing. Not because the moon is unknowable, because when you do know it, the knowledge is uncomfortable. Start with the one thing everyone instinctively understands about space: the vacuum. The moon has no atmosphere. None. Not a thin one. Not one with the wrong composition. Not one that's just slightly too cold or too hot. Essentially nothing. The lunar surface is exposed to the full vacuum of space, and the numbers make this more concrete than the word vacuum usually conveys. Earth's atmospheric pressure at sea level is about 14.7 pounds per square inch. On the lunar surface, the pressure is roughly 3 times 10 to the negative 15th power of Earth's atmospheric pressure. That is not a typo. The Moon has about a quadrillionth of Earth's atmospheric pressure. There is nothing meaningful there. A few atoms of gas escaping from the surface material, a trickle of particles from the solar wind, a trace of sodium and potassium and helium that scientists technically call the lunar exosphere. For all practical purposes, it is perfect vacuum. That means no air pressure, no wind to carry heat or moisture, no buffer between you and whatever the sun decides to deliver on any given day. No atmospheric scattering of sunlight to give you a gentle blue sky. No sound. Complete silence. On Earth, our atmosphere does an extraordinary amount of work that we never think about. It scatters sunlight, giving us that familiar diffuse glow overhead instead of the harsh, directionless illumination of space. It distributes heat around the planet through wind and weather patterns. It burns up most of the small rocks falling from space before they reach the ground. It absorbs a significant fraction of the radiation streaming in from the sun and from the rest of the galaxy. It provides the pressure baseline that every biological process in your body depends on. The Moon has none of that. So if you're standing on the lunar surface, you are standing in a vacuum with no protection between you and open space except whatever suit and habitat you brought with you. The moment your suit fails, the moment the pressure differential becomes your direct physical reality, you are in immediate and irreversible trouble. Not slowly. Not with warning or grace. The physics of a vacuum, acting on a body calibrated for 1 atmosphere of pressure, is not subtle. This is not science fiction. This is straightforward biology and fluid mechanics, and the outcome is not ambiguous. And the terrifying part is that a suit failure, for all its drama, is not actually the hardest problem. It's just the most obvious one. There are problems that are far less intuitive and in many ways far more difficult to solve. The first one is the dust. Lunar dust sounds almost quaint, like something you'd brush off a windowsill. It is nothing like that. The Moon has been bombarded by micrometeorites for 4.5 billion years. With no atmosphere to slow those impactors down, and no water or wind to smooth and erode the surface afterward, each impact shatters the target rock into tiny fragments. Over geological timescales, this process, called impact gardening, has churned and pulverized the entire lunar surface to a depth of several meters in most places. The result is a layer called the regolith, a loose, fine blanket of ground-up material that covers the entire Moon. In the highlands, the lighter-colored ancient terrain, it's typically 4 to 10 meters deep. In the darker flat plains called the mare regions, ancient volcanic outflows that cooled billions of years ago, it can be up to 15 meters deep. And the particles that make up this regolith are not smooth. On Earth, rocks and sand get worn down over time. Water, wind, tumbling against other particles in rivers and on beaches. These processes round off jagged edges, polish away the sharpest points, create the kind of fine, smooth-grained sand that you might walk across on a beach without a second thought. The Moon has none of those processes. Every grain of lunar regolith has the same sharp edges and angles it was left with when the impact that created it occurred. Some particles are partially glassy, formed when the intense heat of a micrometeorite impact briefly melted the surface material before it refroze into irregular glassy shapes. These are particularly abrasive, and every surface particle carries an electrostatic charge from the constant bombardment of the solar wind, which strips electrons from surface atoms and leaves the dust particles electrically active, ready to attract and cling to anything they contact. It clings to everything, to suits, to equipment, to surfaces it has no apparent physical reason to stick to. The Apollo astronauts discovered all of this within hours of their first moonwalks. Harrison Schmitt, the geologist who flew on Apollo 17 and was one of the last two humans to walk on the moon in December of 1972, developed what he described as lunar hay fever almost immediately after returning from the surface. His eyes watered, his throat was irritated, his nose ran constantly. He was reacting to dust particles that had made their way into the cabin after the moonwalk, despite every precaution the mission design had incorporated. The suits came back from the surface, so coated in the material that some of the reflective thermal coatings were noticeably darkened. The dust had worked its way into every seam, every joint, every hinge mechanism. The visor on Schmidt's helmet was scratched by it. Multiple pieces of equipment were degraded. Dave Scott, on Apollo 15, found that the drill they were using to collect core samples had jammed repeatedly because dust had infiltrated the mechanism. Alan Bean, on Apollo 12, accidentally pointed the television camera toward the sun while setting it up, burning out its sensor and ending all live television coverage of the mission after just a few hours on the surface. Now think about what that means for a permanent settlement. If you're living on the moon, you're going outside regularly. Every maintenance trip, every agricultural check, every equipment inspection, every excursion brings dust back in. Every time it makes its way into your airlock, your habitat, your mechanical systems. The particles are small enough to be inhaled, and because of their sharp, irregular, glassy shape, they don't pass through the respiratory system the way ordinary dust does. They embed themselves in lung tissue. On Earth, silicosis is a serious and well-documented occupational disease caused by breathing fine crystalline silica particles, the kind found in mine dust. Stone-cutting operations, tunneling, and certain construction environments. The mechanism is well understood. Sharp particles lodge in the alveoli, the tiny air sacs of the lungs where oxygen exchange happens. The immune system recognizes them as foreign and mounts an inflammatory response. But the particles are not biodegradable. The immune cells, trying to break them down, cannot do so. They are lost in the attempt, releasing inflammatory signals that trigger more immune activity. Over years, the accumulation of these inflammatory responses creates scar tissue in the lungs. The scar tissue progressively reduces the flexibility and gas exchange capacity of the lung tissue. The lung becomes stiff and less effective. Advanced silicosis is a terminal condition, and no treatment currently reverses the damage. Lunar dust is suspected to be worse than the crystalline silica that causes silicosis on Earth. The particles are more reactive, having never been weathered into anything the human immune system has evolutionary experience defending against. The glassy particles carry a higher surface energy, making them more chemically reactive when they contact biological tissue. Laboratory studies, using simulated lunar regolith, materials engineered to match the physical and chemical properties of actual lunar soil, have shown that it can destroy lung cells in culture at lower concentrations than terrestrial silica dust. The particles cause oxidative stress, inflammation, and DNA damage in cell lines exposed to them. Researchers have found that lunar dust simulants are capable of generating reactive oxygen species when they contact biological tissue. These reactive oxygen species are chemically aggressive, damaging cell membranes, proteins, and DNA. Nobody has been exposed to lunar dust long enough to observe the chronic effects in humans. Apollo astronauts inhaled some and had no immediately apparent respiratory consequences. But no immediate consequence and no long-term consequence are very different statements. A person living on the moon for years, repeatedly taking brief exposures to small quantities of dust, might not notice anything wrong until the damage is already significant. And the dust doesn't just threaten your lungs. It threatens everything mechanical. Every suit seal, every joint mechanism, every optical surface, every electronics component is vulnerable to dust infiltration over time. The abrasive, charged particles work their way into gaps that seem too small to allow them through. They scratch lenses, jam moving parts, infiltrate electrical contacts. The optical systems on suits and equipment that are scratched by dust become less effective. Cameras, solar panels, solar cells all lose efficiency as dust accumulates on their surfaces. And unlike dust on Earth that rain or wind eventually clears away, there's nothing on the moon to clean surfaces. Whatever accumulates stays until you actively remove it. Keeping equipment functional in a dusty environment where the dust never settles. Because there's no wind, no rain, no natural process to consolidate it, is an engineering problem that doesn't yet have a satisfying solution. You can design better seals, create dedicated dust-free zones within your habitat, use electrostatic deflection systems to keep dust off critical surfaces, develop specialized coatings. All of that helps. None of it eliminates the problem. The dust is everywhere. It has been accumulating and spreading across the lunar surface for 4.5 billion years. It will be there long after any colony you build, probably long after any human-made structure has crumbled. The moon was dusty before we arrived, and it will be dusty long after the last human leaves. Consider the temperature. The moon has no atmosphere to absorb solar energy uniformly, no winds to distribute heat across the surface, no oceans to act as thermal reservoirs that buffer temperature swings. The result is temperature extremes on the lunar surface, among the most severe of any solid body in the solar system. During the lunar day, when the sun is overhead at equatorial latitudes, temperatures on the surface can climb to around 260 degrees Fahrenheit, about 127 degrees Celsius. Hot enough to boil water. Hot enough that exposed metal surfaces become too hot to touch even through a well-insulated glove. Hot enough that the thermal expansion of materials under direct sunlight becomes a significant engineering consideration. During the lunar night, temperatures drop to around negative 279 degrees Fahrenheit, about negative 173 degrees Celsius. At the equator. That is staggeringly cold. Colder than the surface of Mars, which has at least a thin atmosphere to provide some thermal buffering. Colder than any naturally occurring place on Earth's surface, even the Antarctic plateau in winter. Cold enough that some gases that would otherwise float away condense onto the surface, and cold enough that many materials used in engineering become dangerously brittle. And here's the aspect of this that makes it particularly brutal from an engineering standpoint. A single lunar day-night cycle lasts about 29.5 Earth days. Not a 24-hour cycle. A cycle measured in weeks. 2 weeks of continuous sunlight and building heat, followed by 2 weeks of total darkness and extreme cold. Every material in your habitat, in your equipment, in your power systems, in your suits, in your infrastructure, has to survive cycling through that range, repeatedly, indefinitely. Metal expands in heat and contracts in cold. This is thermal expansion and contraction, and every engineer who works with structures knows it as one of the fundamental stresses any material faces in temperature-variable environments. On Earth, bridges are built with expansion joints to allow for the relatively modest temperature swings between summer and winter. Buildings are designed to handle thermal stress. Pipelines have carefully engineered accommodations for temperature-driven length changes. The temperature range on the lunar surface, nearly 540 degrees Fahrenheit, about 300 degrees Celsius, between the extremes, is far beyond anything Earth-based engineering normally deals with. Cycle through that range enough times, and you get metal fatigue at stress concentration points. Seals that function at one temperature, failing at another. Joints that were tight when warm, developing play when cold. Plastics and polymers that are flexible at room temperature, becoming brittle and cracking at cryogenic temperatures. Adhesives, coatings, and bonding materials, failing as the differential thermal expansion between different materials tears them apart at interfaces. Solar panels, the natural first choice for power generation on the Moon, given the plentiful sunlight, produce no electricity during the 2 weeks of darkness. Zero output for 2 weeks out of every 4. That means you need to store roughly 2 weeks of your settlement's entire energy consumption, including heating, lighting, life support systems, computers, agricultural systems, and manufacturing. The sheer scale of energy storage required for even a modest settlement across 2 weeks of darkness is substantial. Battery technology has advanced significantly in recent years, driven largely by the electric vehicle industry, but the energy density and the total capacity needed for a lunar settlement would push well beyond what current battery systems can practically provide. A different approach is to locate your settlement at one of the lunar poles, where certain ridge and peak locations experience near-continuous sunlight even as the surrounding terrain cycles through darkness. These so-called peaks of eternal light, identified from orbital observations, receive sunlight for 80% or more of the lunar year. They're not perfectly continuous. There are brief periods of shadow, even at the best locations, but they're dramatically more favorable than equatorial or mid-latitude sites. This is one of several reasons why the lunar South Pole has emerged as the leading candidate location for a future permanent settlement. The combination of near-continuous sunlight at certain elevated positions, nearby permanently shadowed craters harboring water ice deposits, and relatively stable temperatures compared to equatorial regions makes it the most favorable location we've identified. Nuclear fission reactors are the other practical power option. They produce steady power regardless of sunlight and are entirely independent of day-night cycles. NASA's Kilo Power project developed a small fission reactor concept that could provide up to 10 kilowatts of power, roughly equivalent to the power used by several typical homes. More advanced designs currently being developed under the Fission Surface Power project aim for 40 kilowatts or more, enough to meaningfully power a small settlement. But bringing fission reactors to the Moon involves a cascade of its own challenges. Safe launch procedures for hardware containing radioactive fuel, with robust safeguards against launch vehicle failure. Heat rejection from the reactor in vacuum, because without air convection or water cooling loops, you must radiate waste heat into space, which requires large radiator panels deployed on the lunar surface. Long-term fuel sourcing and replacement strategies. Radiation management around the reactor. All solvable. None simple, all adding to the complexity and cost of the settlement. The radiation problem is the one that occupies space medicine researchers most consistently, and for good reason. On Earth, you have two layers of protection against the constant stream of radiation flowing through the cosmos. The first is the magnetosphere, a vast magnetic field generated by the churning motion of liquid iron in Earth's outer core. This field extends tens of thousands of miles into space. It deflects most charged particles before they can reach the surface, channeling them around the planet, and in some cases, funneling them toward the poles where they create the aurora. The second is the atmosphere, a column of air above you that, in terms of radiation shielding, is roughly equivalent to about 33 feet of water in shielding capability. It absorbs and scatters radiation that makes it through the magnetosphere. Together, these two systems reduce your radiation exposure at Earth's surface to a background level that biological life has evolved to handle over hundreds of millions of years. The Moon has neither. No global magnetic field worth mentioning. The Moon does have small, localized magnetic anomalies in the ancient crust, remnants of ancient field sources that no longer operate. But these provide no meaningful protection at the scale needed. And no atmosphere. The surface of the Moon is exposed directly to everything space delivers. And space delivers quite a bit. There are two main sources of radiation for a lunar resident to contend with, and they're different enough in character that they require different mitigation strategies. The first is solar radiation. The sun constantly emits a stream of charged particles, mostly protons and electrons, flowing outward at hundreds of miles per second. This background solar wind carries a relatively modest radiation dose that can be blocked by a few centimeters of material. A well-designed spacesuit handles the background solar wind reasonably well. A habitat wall handles it even more comfortably. But the sun is not always in a steady, predictable state. Occasionally, magnetic field lines on the solar surface reconnect in events called solar flares, releasing enormous bursts of energy and charged particles into space in minutes to hours. Even more energetic are coronal mass ejections, events in which the sun launches billions of tons of magnetized plasma into space in a single powerful burst. These events don't affect Earth significantly because our magnetosphere deflects the particles. On the Moon, there's no magnetosphere to deflect them. When a major solar particle event is aimed toward the Earth-Moon system, the energetic particles arrive at the lunar surface within hours to a day or two of the initial event. During a major solar energetic particle event, radiation levels on the lunar surface can spike rapidly to doses that would cause acute radiation sickness within hours of exposure. Acute radiation syndrome at moderate doses produces nausea, vomiting, fatigue, and suppression of bone marrow activity that reduces the immune system's effectiveness. At higher doses, the syndrome becomes life-threatening. A large event could deliver a dose to an unprotected person on the lunar surface that would be potentially fatal. Apollo astronauts were acutely aware of this risk during their brief surface missions. Solar activity was closely monitored throughout each mission. Mission planners carefully timed the surface stays to avoid periods of elevated solar activity, and mission controllers tracked solar conditions continuously throughout every moonwalk. No major solar particle event occurred during any of the Apollo surface stays. That was partly good planning and partly good fortune. You cannot fully predict when the sun will produce a major event. Solar scientists can identify the conditions that make energetic events more likely, and they can give warnings of hours to a day when an event begins. But you can't plan years of operations around avoiding solar particle events entirely. A permanent settlement would need hardened shelter with substantial shielding, where occupants could take refuge rapidly when a solar event warning is issued. Getting everyone inside and into the sheltered area would need to happen quickly within the warning window that solar monitoring provides. The second source of radiation is far harder to address and in some respects more insidious: galactic cosmic rays. These are extremely high-energy particles, mostly protons, but also the nuclei of heavier elements like carbon, nitrogen, oxygen, silicon, and iron, that have been stripped of their electrons and accelerated to near light speed by distant, violent events in the galaxy and beyond. Supernovae, the energetic ends of massive stars, neutron-star mergers, the powerful jets and shock environments around black holes. These particles stream in from every direction, all the time, without pause, with energies that dwarf those of solar particles by factors of millions in some cases. They carry so much energy that they penetrate deeply into almost any shielding material you could realistically use. And the physics of shielding against them is genuinely counterintuitive. When a high-energy cosmic ray particle hits a dense shielding material like lead or iron, it doesn't simply stop. It smashes into the atomic nuclei of the shield material and fragments both itself and those nuclei, producing a spray of secondary particles, protons, neutrons, gamma rays, and lighter nuclei that scatter outward from the interaction point. This shower of secondary particles is called spallation. In some configurations, this secondary radiation is more biologically damaging than the original cosmic ray would have been, because it spreads the energy more widely and includes biologically disruptive particle types. This counterintuitive result means that simply adding more metal shielding around a habitat does not necessarily reduce your radiation exposure from galactic cosmic rays. In fact, too much dense shielding can make things worse. The materials that work best against galactic cosmic rays are hydrogen-rich, such as water, polyethylene, and certain hydrogen-containing plastic formulations, because hydrogen nuclei are small enough that the spallation products are less numerous and less energetic than those produced by heavier nuclei. Even with optimal shielding, you cannot stop galactic cosmic rays entirely with any realistic mass of material. The most energetic cosmic rays will punch through anything. What good shielding does is reduce the dose to manageable levels for most of the particle flux. An astronaut on the lunar surface, inside a reasonably well-constructed habitat with appropriate shielding, receives significantly more radiation annually than an astronaut on the International Space Station. The ISS orbits within the protective reach of Earth's magnetosphere. The Moon sits outside it. The numbers are not precise because they depend heavily on shielding configuration, location on the Moon, solar activity cycles, and individual biological factors. But rough estimates suggest that the surface radiation environment on the Moon, without substantial shielding, would deliver doses in the range of several hundred millisieverts per year. With good underground shielding, that can be reduced to perhaps 100 to 200 millisieverts annually. For context, the average background radiation exposure on Earth's surface is a few millisieverts per year. The occupational dose limit for radiation workers in most countries is 20 millisieverts per year. The annual dose that begins to show measurable increases in cancer risk is estimated to start in the range of 100 millisieverts and above. A person living on the Moon, even in a well-shielded underground habitat, would be accumulating dose at a rate significantly above what would be acceptable in any Earth-based occupational setting. Over a decade, the accumulated dose would represent a meaningful increase in cancer risk. Beyond cancer, radiation biology research is uncovering other effects that become increasingly relevant for long-duration exposure. Central nervous system effects are among the most concerning findings from recent research. Studies on mice and other animals exposed to radiation environments, simulating what would be experienced in deep space or on the lunar surface, have found impairments in spatial memory, reduced learning ability, and changes in behavior that persist long after the exposure ends. The mechanism appears to involve both direct damage to neurons and ongoing inflammation in brain tissue, driven by microglial activation. Microglia are the immune cells of the central nervous system, and chronic activation of them by radiation-induced damage leads to neuroinflammation that can impair cognitive function. A study published in Scientific Reports found that mice exposed to simulated galactic cosmic ray levels showed reduced performance on cognitive tasks and signs of brain inflammation that were still detectable months after the exposure. Whether these findings in rodents translate directly to humans at relevant doses is still being studied. But the direction of the evidence is concerning enough that NASA lists central nervous system effects as one of the priority risk areas for long-duration human spaceflight. Cataracts are another documented consequence of elevated radiation exposure. Apollo astronauts have a higher incidence of cataracts compared to non-astronaut controls, and those who traveled beyond low Earth orbit through the Van Allen radiation belts show higher rates still. Cataracts are treatable with surgery, but for a settlement far from comprehensive surgical support, any condition that impairs vision is a significant concern. Cardiovascular damage is increasingly being studied. Energetic particles traveling through blood vessel walls and heart tissue can damage the endothelial cells lining the arteries, potentially accelerating the development of atherosclerosis. Some retrospective studies on Apollo astronauts have found elevated rates of cardiovascular events compared to non-astronaut controls, though sample sizes are small enough that statistical uncertainty is high. The solutions that work best for radiation protection involve going underground. A meter or two of lunar regolith on top of your structure provides shielding roughly equivalent to Earth's atmosphere for most radiation types. It doesn't solve the galactic cosmic ray problem completely, but it reduces the dose substantially. Several serious habitat concepts for permanent lunar settlement call for either burying prefabricated modules under regolith using robotic earth-moving equipment, having construction robots pile regolith over inflatable structures after they're deployed, or utilizing lava tubes. The Moon has extensive underground tunnel systems formed by ancient volcanic activity billions of years ago. As lava flowed across the early lunar surface, the outer layers of the flow cooled and hardened into a crust, while the inner portion continued to flow. When the flow eventually drained out, it left an empty tunnel, a lava tube. Orbital gravity measurements and surface observations have identified signatures of these structures across the lunar surface. Some appear to be enormous. Recent analysis of gravity data from GRAIL, NASA's Gravity Recovery and Interior Laboratory mission, suggests that some lunar lava tubes could have widths of a mile or more and remain structurally stable due to the low lunar gravity and the absence of the water-driven weathering processes that collapse lava tubes on Earth relatively quickly. Lava tubes would be geologically stable, protected from radiation by meters of overlying rock and regolith, shielded from the temperature extremes of the surface by the insulating rock above them, and potentially large enough to house significant settlement infrastructure. Some researchers consider them the most promising sites for large-scale permanent lunar settlement. The challenge is that we haven't yet explored them directly. We know they likely exist from orbital data, but we don't yet have confirmed access points, structural assessments of specific tubes, or detailed maps of their interiors. That exploration would need to happen before any serious settlement planning could be directed toward them. Then, there's the gravity. The Moon's surface gravity is about 1/6 of Earth's. If you weigh 180 pounds on Earth, you weigh 30 pounds on the Moon. That sounds like a benefit. You'd feel light, almost floating. You could jump approximately 6 times higher than you can on Earth. Moving heavy objects would require a fraction of the effort. In the short term, in the way the Apollo astronauts experienced it during their 3-day visits, low gravity is actually somewhat enjoyable. Watch the footage from the lunar surface, and you see astronauts bounding around in a way that looks almost playful, covering ground with each stride in a way that would be impossible on Earth. But for anyone who stays on the Moon for months, years, or permanently, low gravity is one of the most insidious long-term threats to human health that exists. The human body is not a fixed object. It is a dynamic system that continuously remodels itself in response to the demands placed on it. One of the most important of those demands is mechanical loading, the forces generated by gravity pulling on your mass, and the muscular forces generated to move and support yourself against that pull. Your bones are alive. They are not static structural members, like steel beams in a building. They are continuously remodeled throughout your life by 2 types of cells working in dynamic balance. Osteoblasts are cells that synthesize new bone tissue, laying down the collagen matrix and mineralizing it with calcium phosphate crystals. Osteoclasts are cells that break down bone tissue, dissolving the mineral and digesting the matrix. Under normal Earth gravity, the mechanical stress of simply standing, walking, and moving keeps these 2 cell types in approximate balance in healthy adults, or tips the balance slightly toward building in younger people. When mechanical loading decreases, when gravity pulls less hard on your mass and your muscles have to work less to move you, the balance shifts. Osteoclast activity remains relatively high, driven in part by biological signaling that is less dependent on mechanical load, while osteoblast activity drops in response to reduced mechanical stimulation. The body interprets reduced mechanical stress as a signal that it doesn't need to maintain as much bone mass for the structural demands being placed on it. The result, over months, is progressive bone loss. On the International Space Station, in true microgravity, where there is essentially zero mechanical loading on the skeleton from gravity, astronauts lose bone density at rates of roughly 1 to 2% per month in the most affected regions. These regions are typically the lower back, the hip, the femoral neck, at the top of the thigh bone, and the heel bone. 6 months on the ISS can produce bone loss in these regions equivalent to a decade of normal aging on Earth. This is not a minor effect. In elderly people on Earth, bone density loss at this rate leads to osteoporosis, dramatically increased fracture risk, and significant mortality from fractures that would be trivial injuries in a younger, denser boned person. Astronauts on long ISS missions experience similar bone mineral density after half a year that an elderly person with osteoporosis might have. This is why astronauts on long ISS missions spend 2.5 hours every single day on specialized exercise equipment. The exercise regime typically involves a treadmill with a harness system that loads body weight equivalent forces onto the body, a cycle ergometer for cardiovascular fitness, and a resistance device that allows heavy weightlifting style exercises in microgravity. They exercise that much every single day, just to slow the rate of bone loss, not to prevent it, to slow it. Even with that extraordinary commitment to daily exercise, astronauts still lose bone density during long missions, just more slowly than they would without it. The Moon's 1/6 gravity is not as extreme as the zero gravity of orbital freefall. The mechanical loading on your skeleton is still present. You weigh something. Your legs have to support that weight. But it's dramatically less than what your bones evolved to expect after 4 billion years of life evolving under Earth's gravitational pull. And the critical question, whether 1/6 gravity is sufficient to maintain bone density over years and decades without serious loss, is one that nobody can currently answer with certainty. We have never had a human being live in 1/6 gravity for long enough to know. The Apollo data is useless for this purpose. 3 days on the surface is not enough time to measure the chronic effects of gravitational environment on bone metabolism. Our best models are extrapolations from the microgravity data from the ISS and from bed rest studies on Earth, where research subjects are kept lying down for extended periods to simulate the bone unloading effects of reduced gravity. Those models suggest that 1/6 gravity would produce bone loss significantly more slowly than true microgravity, but still measurably and still progressive over years. Whether that loss eventually plateaus at a level that the person can function with, or whether it continues progressively until it becomes seriously debilitating, is genuinely unknown. Muscle atrophy follows a closely parallel trajectory. Muscles that aren't worked against significant resistance lose mass and strength over time. This is well understood from both spaceflight data and from the experiences of people with conditions that require immobilization or extended bed rest on Earth. In reduced gravity, everyday activities simply don't load your muscles the way they do on Earth. Even the act of standing, which requires your postural muscles to actively maintain your upright position against gravitational pull, requires only 1/6 the muscular effort on the Moon compared to Earth. Climbing stairs, carrying objects, walking from place to place, all of it requires less muscular effort. Over months and years, muscles adapt by reducing their mass to match the actual demand being placed on them. The body is efficient. It doesn't maintain expensive tissue that isn't being used. Without aggressive, specifically targeted exercise regimes, and potentially pharmacological support from drugs and hormones being researched for preventing bone and muscle loss in astronauts, people living on the Moon long-term would progressively become physically reduced compared to Earth-born human norms. There's also the cardiovascular system to consider, and this is where the gravity problem becomes particularly interesting. On Earth, your heart has to pump blood upward against gravity to supply your brain, which sits roughly 18 inches above your heart. This gravitational gradient shapes the cardiovascular system profoundly over the course of evolution. Your blood pressure at your feet, when you're standing, is higher than your blood pressure at the level of your heart, because of the hydrostatic pressure the column of blood above creates. Your blood pressure at your head is lower than at your heart. For the same reason, your autonomic nervous system constantly makes fine-grained adjustments to your heart rate and the tone of your blood vessels to maintain adequate blood supply to the brain across different postures and activities. When you stand up quickly from lying down, Your autonomic system has to rapidly compensate for the sudden increase in the gravitational demand on blood pressure regulation. In lower gravity, these demands are less. Less pumping effort is required to maintain brain perfusion. The hydrostatic pressure gradients are smaller. Over time, the cardiovascular system adapts to the reduced demand, becoming less efficient at the tasks that Earth's gravity demanded of it. Astronauts returning from long ISS missions frequently experience a condition called orthostatic intolerance. When they stand up after landing, their blood pressure drops. They feel dizzy, lightheaded, sometimes nearly lose consciousness. Their cardiovascular systems have adapted to a zero-gravity environment where those rapid compensatory responses were less necessary, and now those systems struggle to perform in Earth's gravity. It typically takes weeks to months of readaptation before full orthostatic function is restored. After years on the Moon, that readaptation might be far more difficult and might take much longer. After long enough, if the cardiovascular system has adapted deeply to 1/6 G, it might not fully return to Earth-capable function. This is what researchers refer to when they talk about the gravity trap. The longer you stay on the Moon, the more deeply your physiology adapts to lunar gravitational conditions, and the harder it becomes to transition back to Earth. Not because anything prevents you from leaving, because your own body, with its extraordinary capacity to adapt to its environment, has reorganized itself around a different gravitational world. And children born on the Moon face an even more fundamental version of this problem. A child developing in 1/6 gravity doesn't have a pre-existing Earth-adapted body to gradually lose. Their skeletal development, their muscular development, their cardiovascular development, their vestibular system that gives them a sense of balance and spatial orientation, all of it would be shaped from the very beginning by 1/6 G. Their bones would grow in forms appropriate to the stresses of a 1/6 G environment. Their hearts would develop for the demands of pumping blood in 1/6 G. Their muscles would develop to match the actual mechanical demands of daily life in 1/6 G. Earth, for them, wouldn't be a place their bodies had forgotten. It would be a place their bodies had never been configured for. Earth's gravity would not feel like home. It would feel like crushing, relentless weight. Their skeletons might literally not be able to support their own weight under Earth's gravitational pull. Their cardiovascular systems might not be able to maintain blood pressure against Earth's hydrostatic gradients. The transition to full Earth gravity for someone who had lived their entire life in 1/6 G could be as medically serious as the sudden application of several times normal gravitational force. People born on the Moon might never be able to visit Earth. Not because of politics or law or economics, because the planet that produced every one of their ancestors would be, for them, physiologically inaccessible. That is a genuinely strange thing to contemplate. A humanity that has divided itself not by nationality or culture or choice, but by gravitational environment. Lunar-born humans who can never experience Earth. Earth-born humans who can visit the Moon, but who, if they stay long enough, may not fully be able to come back. These are not science fiction scenarios. They are the straightforward physical consequences of living in a different gravitational environment for a long time, applied to the real biology of real human bodies. Now add the problem of getting everything you need. The Moon is 238,000 miles from Earth. A journey there takes about 3 days with current propulsion technology. Close enough to run resupply missions in principle. But close enough doesn't mean easy or cheap. Every kilogram of material launched from Earth requires fuel, and fuel is heavy, and lifting mass out of Earth's gravity requires an enormous amount of energy. The energy needed to reach orbit from Earth's surface corresponds to accelerating a mass to about 17,500 miles per hour. And to escape Earth's gravity entirely and reach the Moon requires even more. Launch costs have dropped significantly over the last decade with the development of reusable rocket systems. SpaceX's Falcon 9 and Falcon Heavy have dramatically reduced per-kilogram launch costs compared to the expendable rockets of earlier decades, and the Starship system aims to reduce them further still. But even at the most optimistic future projections, transporting material to the lunar surface remains orders of magnitude more expensive than any other form of freight that has ever existed. And a permanent settlement is not a small or occasional cargo operation. It needs a continuous, reliable, high-volume flow of equipment, spare parts, medical supplies, food supplements, electronics, and consumables to maintain itself. Every kilogram of that supply flow has to be either launched from Earth or produced locally. Producing it locally on the Moon is its own enormous challenge. Start with the most fundamental resource: water. Humans need roughly 2 to 3 liters of water to drink daily. More is needed for hygiene, food preparation, and potentially for growing plants. Water can be split into hydrogen and oxygen through electrolysis, providing both breathable air and rocket propellant. It's a reasonable radiation shield when configured as a liquid water wall around living spaces. Water is, without question, the most important resource any lunar settlement would need to establish locally. For decades, the assumption in planetary science was that the Moon was essentially dry. The samples brought back by the Apollo missions contained almost no water. The lunar surface, bombarded by ultraviolet radiation and without any atmosphere to trap volatiles, seemed to have lost any water it might once have had long ago. But in 2009, a NASA mission called L-CROSS, the Lunar Crater Observation and Sensing Satellite, deliberately impacted a spent rocket stage into the permanently shadowed Cabeus crater near the lunar South Pole, then flew a shepherding spacecraft through the resulting debris plume to analyze what the impact had excavated. The results were clear and significant. Water ice was present in the debris. Spectroscopic measurements of the plume indicated a water content of approximately 5.5% by mass in the excavated material. This was not a trace amount. This was a meaningful water concentration in a specific location. Subsequent orbital observations from the Lunar Reconnaissance Orbiter, India's Chandrayaan missions, and other assets have progressively built a more detailed picture of lunar water distribution. The Sophia Airborne Observatory detected water molecules in the spectral signatures of sunlit areas of the lunar surface, suggesting that water is more widely distributed than just in the cold trap. NASA's Mini-RF radar instrument has mapped subsurface structures in polar regions consistent with water ice deposits. There is water on the Moon. The South Pole region, in particular, appears to have substantial deposits in and around several permanently shadowed craters. That is potentially transformative for a permanent settlement. A local water source changes the resource equation fundamentally. It means local oxygen for life support, local hydrogen for rocket propellant, local radiation shielding material, local water for agriculture. It means the most critical consumable doesn't have to be launched from Earth. But extracting that water is not a simple matter of digging it up. Those permanently shadowed craters are permanently shadowed because they sit in depressions at high enough latitudes and with steep enough surrounding terrain that the sun's light never reaches their floors, which means they're among the coldest places in the entire solar system. Temperatures inside Cabeus and similar craters hover around -220 to -240 degrees Fahrenheit, roughly -140 to -151 degrees Celsius. Some measurements suggest even colder in the deepest shadowed areas. Operating mining equipment at those temperatures is a serious engineering challenge. Most lubricants solidify at cryogenic temperatures, making any mechanism with moving parts prone to jamming or seizing. Metal becomes brittle and more prone to fatigue failure. Electronics, particularly those containing capacitors and certain semiconductor components, can behave erratically or fail at extreme cold. Battery systems, essential for powering mobile equipment, deliver dramatically reduced capacity at cryogenic temperatures. The solar panels that normally power surface equipment produce absolutely nothing inside a permanently shadowed crater because there is no sunlight. Power for mining operations in these craters would need to come from cables routed from solar panels on nearby sunlit ridges or from compact nuclear power sources brought into the shadowed area. The terrain inside these craters is rough, largely unmapped at the resolution needed for safe robotic operations, and entirely uncharacterized at the subsurface level. Robotic miners and excavators would need to navigate uncertain terrain in total darkness, at extreme cold, while managing power logistics and avoiding subsurface hazards. This is a genuinely difficult robotic challenge that has not yet been demonstrated even in laboratory analogues, let alone in actual cryogenic vacuum conditions. Beyond the water deposits, the lunar regolith contains a variety of other resources that become relevant for a self-sustaining settlement. Oxygen is the most abundant element on the lunar surface, locked up in silicate minerals and metal oxides. It's everywhere, in every rock, in every grain of regolith. The challenge is that it's chemically bound and has to be extracted through high-temperature or electrochemical processes. The European Space Agency has been developing and testing a process called molten regolith electrolysis, in which regolith is melted at very high temperatures and an electrical current is passed through the melt, causing the oxygen bound in metal oxides to be released as gas. A useful byproduct of this process is liquid metal, primarily iron and aluminum, which could itself be used for construction. Laboratory demonstrations of this process at reduced scale have been successful. Scaling it to industrially useful production levels and operating it reliably in the actual lunar environment remains a development challenge. Silicon, present in abundance in the regolith silicate minerals, could theoretically be refined and used to produce solar panels directly on the Moon, eliminating the need to transport them from Earth. The iron and titanium in the Mare regions are present in concentrations that would be considered valuable ores on Earth. Aluminum, magnesium, calcium, and other structural metals are present in the Highlands material. Helium-3, an isotope of helium, essentially non-existent on Earth's surface, has accumulated in the lunar regolith from billions of years of solar wind bombardment. Some estimates suggest the Moon contains on the order of 1 million tons of this material embedded in the near-surface regolith. If controlled fusion reactors using helium-3 fuel are ever developed, this represents an energy resource of extraordinary scale. Some economic analyses of lunar resource development place the potential value of the Moon's helium-3 reserves in the tens of trillions of dollars. Whether any of these lunar resources represent economically viable opportunities given the extraordinary cost of operations on the Moon, is still an open question. But it's increasingly an open question that serious economic analysts are engaging with as the cost of access to the lunar surface continues to decrease. Food is a dimension of the challenge that's easy to underestimate when you're imagining the adventure of living on the Moon. For a permanent settlement, you simply cannot rely indefinitely on packaged food launched from Earth. You need to grow at least some of your food locally to achieve any meaningful degree of self-sufficiency. Plants need light, water, nutrients, carbon dioxide, and a growing substrate. The Moon provides none of these in usable form without significant human intervention. Light is available during the 14-day lunar day, but it's unfiltered solar radiation, high in ultraviolet wavelengths that are damaging to plants, and arriving in a cycle completely wrong for most crop species. Most food crops evolved for a 24-hour day-night cycle and have biological clocks calibrated to that rhythm. 2 weeks of continuous light, followed by 2 weeks of darkness, would disrupt plant growth cycles, affect flowering and fruiting, and potentially trigger stress responses. Growing under controlled artificial lighting, using LED systems tuned to the wavelengths plants use most efficiently, is the more practical approach. It allows precise control of the light-dark cycle, the light spectrum, and the intensity. But it requires substantial electrical energy, which has to come from either solar power, nuclear power, or a combination. Water has to come from whatever local sources can be tapped, primarily the water ice deposits in the shadowed polar craters, if they can be mined effectively. Carbon dioxide, the raw material that plants use in photosynthesis to build their mass, would need to be managed carefully in the closed habitat environment. In a sealed system, you want enough carbon dioxide to support active plant photosynthesis, which actually operates best at carbon dioxide concentrations higher than the roughly 400 parts per million in Earth's atmosphere. But you also need to ensure the carbon dioxide level doesn't rise high enough to cause problems for the humans living in the same enclosed space. Managing this balance in a closed-loop life support system is a solvable engineering problem, but it requires active monitoring and control. Nutrients represent the most complex challenge for lunar agriculture. On Earth, healthy agricultural soil is not merely a physical substrate. It's a complex biological ecosystem composed of bacteria, fungi, archaea, nematodes, earthworms, and countless other organisms that transform raw minerals and organic matter into forms that plant roots can absorb. Nitrogen-fixing bacteria convert atmospheric nitrogen into ammonia that plants can use. Mycorrhizal fungi form symbiotic relationships with plant roots, dramatically extending their effective reach and improving nutrient uptake in exchange for sugars the plant produces. Decomposer organisms break down organic matter from dead plants and animals into simpler compounds that cycle back into the soil nutrient pool. Lunar regolith has none of that. It's a physically and chemically hostile growing medium that has been sterilized by billions of years of radiation, never had any life within it, and lacks the organic carbon, nitrogen compounds, and biological community that makes Earth's soil capable of supporting plant growth. It contains reactive compounds, including perchlorate salts that are toxic to many organisms at elevated concentrations. It may contain reactive oxygen species from solar wind exposure. Its chemical and mineralogical composition varies across the lunar surface, and some compositions may be more hostile to plants than others. The most direct evidence of these challenges came from a study published in May of 2022 by researchers at the University of Florida who obtained actual Apollo-returned lunar regolith samples and grew a small flowering plant called Arabidopsis thaliana in them. This is a small plant in the mustard family that serves as the standard model organism for plant biology research, the equivalent of the laboratory mouse for animal biology. The plants grew. That was the important finding, that growth was possible at all in actual lunar regolith. But the plants showed unmistakable signs of stress. They were smaller and grew more slowly than controlled plants, grown in terrestrial soil or in lunar simulant materials made from Earth rocks. Gene expression analysis showed the plants were activating stress response pathways associated with salt stress and oxidative stress. The plants grown in regolith from more heavily radiation-exposed areas of the Moon, where decades of cosmic ray bombardment had altered the surface chemistry, did significantly worse than those grown in regolith from less exposed areas. Making lunar regolith into productive agricultural soil would require extensive amendment over time. Adding nitrogen in plant-accessible form, either through chemical fertilizers or through nitrogen-fixing microbial communities. Adding phosphorus and potassium. Incorporating organic carbon from composted plant and food waste to build up the soil organic matter that supports microbial communities. Managing and potentially neutralizing the toxic perchlorate compounds. Introducing appropriate microbial communities to begin the soil biological processes that make nutrient cycling possible. This is feasible. Soil science on Earth regularly involves rehabilitating degraded or contaminated soils, and the tools and knowledge exist. But it's a years-long process before you'd have truly productive agricultural soil. Hydroponic and aeroponic growing systems, where plants grow with their roots either in nutrient-rich water solutions or misted with nutrient-containing water without any soil substrate, offer a more immediately deployable approach. These systems have been used successfully on the International Space Station, producing lettuce, radishes, kale, and other fast-growing leafy crops. They're controllable, they don't depend on developing soil biology, and they use water and nutrients efficiently. But they require more intensive engineering. They're more sensitive to system failures than soil-based growing, and they produce primarily leafy crops rather than the calorie-dense staple crops like wheat, rice, and potatoes that make up the bulk of human nutrition. A genuinely self-sufficient food system for a lunar settlement would need to incorporate a range of approaches. Hydroponic systems for high-value nutritional crops that can be produced quickly. Gradually developed soil systems for more diverse agriculture over the longer term. Closed-loop nutrient cycling that captures and reprocesses the nutrients from food waste, human waste, and plant waste back into the growing system. Possible insect farming for protein, as insects convert organic waste into protein with far greater efficiency than conventional livestock. And all of it maintained in a closed-loop system that doesn't continuously require inputs from Earth. This is technically achievable. It is not technically simple. And any failure in the food production system, without adequate emergency reserves, creates an immediate, life-threatening situation. Think about something as basic as construction. Building on the Moon means working in a spacesuit. Every bolt tightened, every panel lifted, every connection made, every instrument installed, happens through pressurized gloves that resist every motion your hands make. The physical exhaustion of glove work that the Apollo astronauts documented after just a few hours would be the daily experience of the workforce building a lunar settlement. There's a reason why a great deal of serious lunar settlement planning relies heavily on robotic construction. The idea is that robots do the heavy lifting and structural assembly, while humans supervise, handle complex decision-making, and intervene when something unexpected happens. Robotic construction technology has advanced enormously in recent years, driven by both the space industry and Earth-based applications. NASA's work on autonomous systems, the advances in robot manipulation from the robotics research community, and the growing maturity of autonomous vehicles all point toward increasingly capable robotic construction systems. But robots in actual space environments are not yet the confident, reliable, fully capable machines that optimistic timelines sometimes assume. They operate more slowly than human workers. They require careful programming for every anticipated task and human intervention when they encounter situations outside their programmed scenarios. They break down and need repair. Remote operation from Earth introduces the round-trip communication delay of about 2.5 seconds between Earth and the Moon. For slow, deliberate, robotic construction tasks, 2.5 seconds is manageable. For tasks requiring real-time fine manipulation or rapid response to unexpected situations, it is not. Autonomous operation at the level needed for complex construction tasks requires artificial intelligence systems that are still maturing. 3D printing with regolith is one of the most promising construction approaches. The idea is to use robotic systems equipped with large-scale additive manufacturing capability, essentially 3D printers that extrude or sinter regolith into solid structural forms. Several processes have been proposed and partially demonstrated in laboratory settings on Earth. One approach heats the regolith until it sinters, fusing the particles into a solid mass without fully melting them. Another uses microwave energy to melt the surface layer of a regolith bed, and then allow it to solidify, building up structure layer by layer. A third uses chemical binders to consolidate regolith into a concrete-like material. Tests of these approaches using lunar regolith simulants on Earth have produced encouraging results in terms of the structural properties of the products. The challenge is operating these systems reliably in the actual lunar environment, with actual lunar regolith, using equipment that has to function in vacuum, handle the temperature extremes, cope with dust infiltration, and operate with minimal human intervention. Demonstrating something in a climate-controlled laboratory on Earth and building a structurally sound radiation shield in a permanently shadowed polar crater on the Moon are very different engineering achievements. The most promising construction strategy for a near-term lunar settlement is probably a combination of approaches. Prefabricated habitat modules designed and built on Earth, launched to the Moon, and landed or assembled robotically. Regolith piled over them by robotic equipment to provide radiation shielding and thermal insulation. Gradual addition of locally manufactured components as manufacturing capability is established. Progressive expansion of the covered, protected living and working volume as the settlement grows. This approach reduces the dependence on locally manufactured structural elements during the initial phase, when manufacturing capability doesn't yet exist. It accepts higher launch mass costs in exchange for reliability and faster establishment of a viable habitat. Over time, as resource extraction and manufacturing capability develop, the dependence on Earth-launched materials for construction can decrease. Communication is a thread that runs through all of this. Not just the communication delay, but the entire infrastructure of staying connected. A permanent lunar settlement would rely on continuous, reliable communication with Earth for mission support, medical consultation, engineering guidance, data downlink for science, software updates, psychological support for the crew, and contact with family members. Maintaining that communication requires a robust link. The moon is never more than about 2.5 light seconds away, so the communication window is always available. But the actual communication infrastructure requires transmitters, receivers, antennas, and the power to operate them. Antennas, on the lunar surface, need to be pointed toward Earth, which requires either tracking systems that move them as the moon rotates, or multiple antennas covering different directions, or relay satellites. From the lunar near side, Earth is always above the horizon, so direct communication is straightforward. From the lunar far side, the natural choice for certain scientific activities, Earth is always below the horizon, and communication requires relay satellites in appropriate orbits. Data rates through current and near-future communication systems are limited. Streaming high-definition medical imaging for real-time surgical guidance, for example, requires much higher bandwidth than ordinary voice and data communication. Laser communication technology, which can achieve much higher data rates than radio frequency systems, is under development and will likely be part of the infrastructure for future lunar operations. All of this communication infrastructure needs to be in place, reliable and maintained before anyone lives permanently on the moon. There is a physiological challenge that rarely makes headlines, but affects the quality and safety of every single day on the moon. Sleep. On Earth, your circadian rhythm, the internal biological clock that regulates your cycles of alertness and rest, is primarily set by light. Exposure to bright light in the morning signals your brain to suppress melatonin, raise cortisol, and promote wakefulness. Dimming light and darkness in the evening trigger melatonin release, a drop in core body temperature, and the transition towards sleep. This system evolved under Earth's 24-hour day-night cycle, and it is deeply embedded in human biology. The moon's natural day-night cycle is 29.5 Earth days long. A habitat at most lunar locations would need to impose an entirely artificial 24-hour schedule on its occupants, because there's no natural cycle of appropriate length to follow. Most serious habitat designs incorporate lighting systems specifically engineered to mimic the spectral and intensity characteristics of natural sunlight at different times of day, cycling through an artificial dawn, daytime, dusk, and nighttime on a 24-hour rhythm. This is technically achievable, and similar systems are used in some polar winter research environments on Earth. But it requires the lighting system to work reliably and to be calibrated correctly. If it fails, or if occupants disrupt their own cycle by using screens or bright lights at the wrong times, circadian disruption follows. Chronic circadian disruption has real health consequences beyond simple tiredness. Research on shift workers and people with sleep disorders has connected disrupted circadian rhythms to increased risk of metabolic disorders, elevated cardiovascular risk, immune suppression, mood disturbance, and impaired cognitive performance. For a settlement where sound judgment matters every single day, and where immune suppression adds to an already elevated risk environment, circadian health is a genuine safety priority. On Earth, stepping outside is nothing. You open a door, you're outside. No preparation, no risk assessment, no procedure. The atmosphere surrounding you is breathable. The temperature is within the range your body can handle. The pressure is what your cells were built for. On the moon, going outside is an operation, not a casual one. Every excursion begins with putting on a spacesuit, and doing that properly takes time. Current spacesuits, The extravehicular mobility units developed for the International Space Station and the newer XEMU designs developed for the Artemis lunar program are essentially individual miniature spacecraft. They maintain internal pressure at about 4.3 pounds per square inch, less than Earth's 14.7, but enough to provide a breathable, pure oxygen atmosphere. They regulate temperature through multiple layers of insulation and through a system of tubes carrying cooled water against the astronaut's skin, connected to a portable life support system that acts as a wearable refrigerator. They filter and supply oxygen from tanks in the life support system. They absorb carbon dioxide through chemical absorbers using materials called lithium hydroxide or other carbon dioxide scrubbers, which have a finite capacity and need regular replacement. They provide some protection against radiation, though limited. They have primary and backup life support systems. They are marvels of engineering. They are also extraordinarily difficult to work in. The gloves are pressurized against the vacuum of space, which means they actively resist every motion your hands make. To close your fingers around something, to grip a tool, to manipulate a fastener, you're fighting the suit's tendency to return to its neutral, pressurized shape. After a few hours of this, your hands are exhausted in a way that's genuinely difficult to describe. Apollo astronauts described their hands cramping severely during long moonwalks. The EVAs became progressively more uncomfortable as hand fatigue accumulated. The suit as a whole restricts movement in every dimension. Bending at the waist is harder. Reaching overhead is constrained by the shoulder geometry. Crouching is possible but takes effort. Even turning your head is somewhat limited by the helmet. All of this makes tasks that would be trivial in regular clothing, such as picking up a small object from the ground, threading a bolt, connecting an electrical connector, become challenging, slow, and tiring. And on the moon, the suit becomes a dust collection system from the moment it touches the surface. Every moonwalk coats the suit's exterior with electrostatically clinging regolith particles. The joints that need to move freely get gritty. The thermal coatings that reflect sunlight get darkened. The optical surfaces of the helmet visor get scratched. All of this is then brought back into the airlock and habitat after each excursion, despite cleaning procedures designed to minimize transfer. For a permanent settlement, the maintenance demands of the suit itself would be substantial and continuous. The chemical absorbers for carbon dioxide need regular replacement. The lithium hydroxide canisters, or equivalent, have a finite lifespan. The seals at every joint need inspection and replacement on schedule. The cooling system needs maintenance. The gloves, which take the most physical abuse, need regular replacement. The suit itself needs systematic inspection and certification before each use. All of this is manageable if you have spare parts, trained personnel, and time to do it properly. A settlement that runs low on spare suit components, or that pushes suits into use beyond their maintenance schedules because there's no time to do it right, is a settlement in increasing danger every time someone goes outside. The medical situation on the moon deserves serious consideration because it differs from anything we currently manage on Earth in a fundamental way. The nearest hospital is a 3-day journey away. That's the minimum transit time with current propulsion technology. For a medical emergency on the lunar surface, 3 days is a very long time. Cardiac arrest causes irreversible brain damage within about 4 to 6 minutes without CPR or defibrillation, and without advanced cardiac life support within the first 15 to 20 minutes, survival rates drop sharply. A stroke causing a large cerebral infarction can lead to irreversible damage within hours. Appendicitis can progress from a manageable inflammation to a perforated appendix and peritonitis, a potentially life-threatening infection of the abdominal cavity within 24 to 72 hours of the initial onset of symptoms. Serious trauma from an equipment accident, a suit failure, a fall on the rough lunar surface can produce injuries requiring immediate surgical intervention. A lunar settlement would need to be its own medical facility for all of these situations, not a clinic. A full medical facility. It would need diagnostic equipment, from basic vital signs monitoring and physical examination tools to imaging capability. On Earth, medical imaging typically requires large, expensive equipment like CT scanners and MRI machines. More portable versions exist, and ultrasound equipment is compact enough to be practical, but the full diagnostic capability of even a modest Earth hospital would be difficult to replicate. It would need surgical capability, including a sterile operating space, anesthesia capability, surgical instruments, and the ability to perform both emergency and elective surgical procedures. It would need intensive care infrastructure, meaning the ability to manage ventilator support, IV medications, continuous monitoring, and the other interventions that keep critically ill patients alive while they recover. It would need a comprehensive pharmacy covering the medications needed for the most common medical emergencies and for the chronic conditions of the settlement population. And it would need the trained personnel to run all of this. That means having physicians and nurses and other health professionals as part of the settlement crew, which takes up slots that might otherwise go to scientists, engineers, or other specialists the settlement needs. The medical challenges don't end with acute care. Chronic disease management becomes increasingly complex in a resource-limited environment far from medical supply chains. Someone with diabetes needs insulin. Someone with hypertension needs antihypertensives. Someone with a thyroid condition needs thyroid hormone replacement. Medications expire, and resupply is expensive and uncertain. Mental health care requires not just pharmaceutical support, but trained counselors and a therapeutic environment, both of which are difficult to maintain in the stressful, confined conditions of a lunar settlement. Dental care is often an afterthought in space medicine discussions, but it shouldn't be. Dental emergencies are common, and they range from painfully uncomfortable to genuinely life-threatening if dental infections are allowed to spread. A cracked tooth, an abscess, a wisdom tooth that needs extraction. All of these are routine procedures at any dental office on Earth. On the Moon, they require a trained dentist, dental equipment, anesthetics, and an available facility, all of which need to be part of the settlement infrastructure. Obstetric care is in a different category from most medical needs because it involves not an illness or injury, but a normal biological process. But it's a process that can go wrong in ways that require immediate expert intervention. Emergency cesarean sections, placental complications, serious postpartum hemorrhage, premature infants requiring neonatal intensive care. If a settlement is large enough and has been there long enough for pregnancies to occur, it needs obstetric and neonatal capability. The research community, working on space medicine, is aware of all of this and actively working on solutions. Telemedicine technology continues to advance, and the vision of a lunar doctor performing a complex procedure guided in real time by specialists on Earth is increasingly technically plausible. The round-trip communication delay of about 2.5 seconds between Earth and the Moon is manageable for slow, deliberate procedures under the guidance of an Earth-based specialist. Autonomous surgical assistance systems, robotic tools that can be guided remotely or that can operate with some autonomy, are a research direction that could extend what's possible. But the honest conclusion is that a lunar settlement would accept a level of medical risk that no Earth-based community would tolerate. People would go, knowing that certain medical situations that would be routinely survivable at home might not be survivable there. That is not a disqualifying fact. But it is something that every person making the choice to live on the moon would have to engage with seriously. The psychological dimension of all of this is perhaps the hardest to convey to someone who hasn't experienced long-term isolation combined with genuine physical risk. The moon is 238,000 miles away. That's close enough that messages arrive with only a round-trip delay of about 2.5 seconds. You can hold a conversation with people on Earth. It's a little stilted because of the pause between sending a message and receiving a reply, but it's a recognizable conversation. This distinguishes the moon from deeper destinations like Mars, where the communication delay is measured in tens of minutes. But the delay isn't the main thing. The main thing is that you are somewhere else. On the International Space Station, you can look out the cupola window and see Earth filling a substantial portion of your view. It's right there, enormous and blue and present. You can see weather systems forming and dissipating. You can see the lights of cities at night. The planet feels close. From the lunar surface, Earth is a beautiful disk in the sky, not a presence. A disk. You are, unmistakably, somewhere else. The confinement would be relentless and difficult to fully imagine from the comfortable vantage of life on Earth. Your world is your habitat. The pressurized interior that you share with your crewmates. The surface outside is immediately lethal without a suit, and going out in a suit is a planned, procedurally intensive operation. You cannot step outside for fresh air. You cannot go for an unplanned walk. You cannot be spontaneously alone in any outdoor environment. You cannot experience weather. You cannot smell rain. You cannot hear wind. You cannot see the sky change or watch clouds move. You cannot experience the kind of natural novelty that Earth delivers constantly, automatically, and without any effort on its part. The habitat's sounds become the ambient soundtrack of your life. The same equipment hums, the same ventilation noise, the same vibrations of life support systems. The faces of your crewmates are the faces you see every day. The same walls, the same corridors, the same view out the same windows. Research on people who live in genuinely isolated, confined environments over extended periods has identified consistent patterns of psychological response. Antarctic winter overcrews, who spend months at research stations with no possibility of evacuation, no outside visitors, and no way to go outside except in extreme cold protective gear, provide some of the best analogues we have for the lunar experience. Studies on these crews have found that mood tends to drop in the third quarter of the winter over period, a phenomenon called the winter over syndrome or third quarter effect. Initial enthusiasm carries people through the first quarter. The novelty and challenge of the second quarter sustains engagement. But in the third quarter, as the accumulated weight of confinement and isolation builds and the end still feels far away, mood drops, irritability increases, interpersonal conflicts escalate, and performance on complex tasks can decline. The fourth quarter brings psychological improvement as the end becomes tangibly close. For a permanent lunar settlement, there is no fourth quarter. There is no end date when things go back to normal. For the people who have chosen to stay permanently, the confinement and isolation are simply the conditions of their life. The people who have studied long-duration isolation most carefully emphasize that social environment matters enormously. Compatible, well-matched group dynamics can make confined environments manageable. Poor group dynamics, interpersonal conflicts that fester without the relief valve of physical distance and time apart, can make even a short, confined mission feel unbearable. Selecting and training a crew for long-term lunar habitation would need to place enormous emphasis on social compatibility and conflict resolution skills, not just technical competence. And even perfect selection doesn't guarantee smooth group dynamics over years, because people change and relationships evolve in ways that no selection process can fully anticipate. Access to meaningful private space within the habitat becomes psychologically important. People need time and space that is genuinely their own, even in a small settlement. Communication with loved ones on Earth needs to be a reliable, protected priority in scheduling, not something that gets squeezed out when operational demands escalate. Autonomy over some aspects of daily life, the ability to make choices that are yours and not dictated by operational requirements, matters for psychological health in ways that can be difficult to protect in an environment where everything is mission-critical. Access to nature, even simulated or minimal, appears to matter. Studies on confined environments have found that access to plants, to natural lighting cycles, to views of anything that isn't a wall, has measurable, positive effects on psychological well-being. For a lunar settlement buried underground for radiation protection, providing even minimal connection to natural visual environments would require deliberate design effort. Meaningful work is perhaps the most important psychological sustainer in isolated environments. People who have a clear sense of purpose, who understand that what they're doing matters and why, cope with confinement and hardship far better than those who don't. A lunar settlement would have no shortage of genuinely important work. The science being done, the engineering challenges being solved, the very project of making the settlement more self-sufficient and resilient, all of it carries genuine significance. Maintaining that sense of meaning and mission through the daily grind of routine maintenance and the psychological weight of cumulative isolation requires deliberate effort and leadership. There's an aspect of the lunar environment that gets less attention than radiation or gravity or dust, but it's just as real. Micrometeorites. The moon's surface has been bombarded by impactors of every size for 4.5 billion years. The large craters are the visible legacy of this. But the bombardment continues today, at smaller scales. Without an atmosphere, even the tiniest particles, dust grains moving at tens of miles per second relative to the moon, reach the surface and impact it directly. Some estimates suggest the moon receives on the order of several tons of micrometeorite material per day, distributed across its entire surface area. At these scales, the impact flux is low enough that a person on the surface during a short moonwalk faces a statistically tiny risk from any individual impact. But over years, a surface structure is collecting statistical exposure. A small micrometeorite punching through a habitat wall at tens of miles per second would create a hole and cause rapid pressure loss. The probability of this happening to any given habitat over a decade is small but non-zero. Redundant pressure barriers, self-sealing materials, rapid leak detection systems, and emergency hull patching procedures are all standard elements of habitat design for this reason. The Apollo landing sites provide interesting data. Analysis of materials left on the lunar surface has found microscopic impact pits and glass deposits from hypervelocity microimpacts. Over geological time, this constant micrometeorite flux is one of the processes that creates and churns the regolith. For a permanent settlement, it's another layer of risk to manage. Not the most urgent one. Not the one that keeps engineers up at night. But real, persistent, and part of the cumulative hazard assessment for any surface structure. There's one more thing to understand about the lunar environment. The Moon is geologically quiet compared to Earth, but it is not geologically dead. Moonquakes happen. NASA's Apollo seismometers, deployed on the surface during the program years and operating continuously from the first installation in 1969 until they were switched off in 1977, detected thousands of seismic events over that period. Modern analysis of that data, combined with more recent orbital observations, has identified 4 main types of moonquakes. Deep moonquakes are the most common. They originate hundreds of miles below the surface and are triggered by tidal forces as the Moon orbits Earth. Just as the Moon's gravity raises tides in Earth's oceans, Earth's gravity distorts the Moon slightly as it orbits. And this periodic squeezing and relaxing generates seismic activity at depth. These deep events are generally small and attenuate significantly by the time they reach the surface. Shallow moonquakes are less frequent but originate closer to the surface. They are caused by thermal stresses in the crust, by ongoing tectonic adjustments from the cooling and contraction of the Moon over geological time, or by other mechanisms not yet fully understood. The shallow moonquakes are the ones most relevant for surface construction. Some have been measured as high as magnitude 5.5. More significantly, they have lasted up to 10 minutes. On Earth, a magnitude 5.5 earthquake causes moderate damage to ordinary buildings, and most earthquakes of any magnitude are over in seconds to a minute or so. 10 minutes of sustained shaking is exceptional. It would place cumulative fatigue, stress on any structure, in ways that an equivalent brief earthquake would not. Moonquakes also caused by meteorite impacts are documented. When a substantial impactor strikes the lunar surface, the shockwave propagates through the regolith and can be detected seismically at considerable distances. These are random events that can't be predicted. Thermal moonquakes occur near the surface as the extreme temperature changes between the lunar day and night cause thermal expansion and contraction in the surface material, generating small seismic signals. These are predictable in their timing, occurring at the transitions between day and night, but they represent ongoing seismic loading of near-surface materials. For lunar construction, seismic resilience means understanding the local seismic environment at the specific site, which requires extended monitoring before major construction begins. It means designing structures with appropriate damping, flexibility, and redundancy in their load paths so that seismic events don't produce catastrophic failure. The unconsolidated regolith presents a particular challenge because loose, granular materials can behave in complex ways under seismic loading, including a phenomenon called liquefaction in wet soils on Earth, where the material temporarily loses its load-bearing capacity. In dry regolith, a simpler form of seismically induced settlement and movement can occur. Foundation design for lunar structures needs to account for this, either by bearing on bedrock, by consolidating the regolith through compaction or sintering, or by designing structures that can accommodate some differential settlement without losing structural integrity. none of these challenges are unsolvable. They are problems that engineers can engage with, given sufficient data about the local environment. But they add to the already long list of things that need to be understood and addressed before people can safely live on the moon. The question that underlies all of this is, why do it? Why accept the dust and the radiation and the gravity trap and the confinement and the medical risks and the food challenges and the seismic uncertainties and the communication delays and the thermal extremes? The honest answer is not a simple one, but it involves several distinct and genuine motivations. The first is scientific. The moon is a record of the early solar system in a way that almost nothing else in our vicinity can match. Its lack of plate tectonics, which, on Earth, continuously recycles crustal material back into the mantle, means that ancient crust survives on the lunar surface. Its lack of significant erosion processes means that surface features from billions of years ago remain essentially intact. Its surface preserves evidence of conditions that Earth has long since erased, impact records going back 4 billion years, ancient volcanic eruptions from the first billion years of the solar system, the chemical record of the solar wind embedded in the regolith, and potentially pristine samples of ancient comet and asteroid material that struck the moon before the inner solar system had evolved to its present configuration. A permanent human presence on the moon, with the ability to conduct geology, collect samples, set up long-term monitoring networks, and explore diverse terrain, would advance our understanding of the early solar system in ways that robotic missions, however capable, cannot fully replicate. The permanently shadowed polar craters add another scientific dimension. The ices and other volatiles trapped there are time capsules from the early inner solar system. Analyzing their chemistry in detail, understanding their isotopic compositions, tracing the sources of the water and other compounds, could provide information about the delivery of water to the early Earth, about the population of comets and asteroids in the early solar system, and about the origin of the volatiles that made our planet habitable. The second reason is astronomical. The lunar farside offers a radio observation environment that exists nowhere else in the accessible solar system. Earth's radio noise, produced by every electronic device on the planet, fills the radio spectrum across a wide range of frequencies. For radio astronomy operating at those frequencies, the noise floor from Earth severely limits what can be observed. A radio telescope array on the lunar farside, permanently shielded from Earth's emissions by the bulk of the moon itself, would have access to frequency ranges that are simply unobservable from anywhere near Earth. Frequencies below about 10 MHz are also blocked by Earth's ionosphere, making them completely inaccessible from Earth's surface regardless of radio interference. On the lunar farside, there's no ionosphere and no interference from Earth. This opens access to the cosmic dark ages, the period from roughly 380,000 years after the Big Bang, when the cosmic microwave background was released, to about 1 billion years after the Big Bang, when the first stars formed and ionized the intergalactic medium. During this period, the universe was filled with neutral hydrogen, and this hydrogen emits and absorbs radiation at a characteristic frequency called the 21 centimeter line. The cosmological redshift stretches this frequency by the expansion of the universe, so the Dark Ages hydrogen appears today at very low frequencies, exactly in the range that a lunar farside telescope could observe. Mapping the distribution of this hydrogen over the cosmic Dark Ages would reveal how matter was distributed in the early universe, how the first structures formed, and provide fundamental tests of our models of cosmology. It's one of the most scientifically significant observations currently impossible to make from Earth. The third reason is strategic. Humanity is currently a single planet species. Every human being who has ever lived has lived on Earth. All of human civilization, all of human culture, all of the accumulated knowledge and art and science and history of our species exists on one fragile planet. On the scale of astronomical time, confining everything to one location has obvious risks. A sufficiently large asteroid impact could substantially damage civilization. A supervolcanic eruption could alter climate for years. On longer timescales, the sun's evolution will eventually make Earth increasingly inhospitable. These are distant concerns, and none of them justifies panic. But they do argue for the long-term importance of not having everything in one place. Establishing a permanent human presence on the Moon, and eventually on other bodies, is the beginning of making humanity a multi-world species. The Moon is the first practical step in that direction, close enough to maintain supply lines and communication, accessible enough to be a genuine test bed for the technologies and knowledge base needed for further expansion. The fourth reason, and perhaps the most honest one, is that exploration is part of what humans do. We have been exploring since we were capable of locomotion. We have followed coastlines, crossed mountain ranges, sailed oceans, dug mines into the earth, ascended to the top of every peak, descended to the bottom of every trench. We have sent probes to the edges of the solar system and robots to the surface of Mars. The impulse to go further, to see what's there, to stand somewhere new and understand it from the inside rather than the outside, is as fundamental to human character as anything we have. The Moon is the next place, not the last. But the next. None of this means that living on the Moon will happen quickly or without serious setbacks. The history of space exploration is a history of extraordinary ambition, punctuated by genuine tragedy. The Apollo 1 fire in January of 1967 took the lives of Gus Grissom, Ed White, and Roger Chaffee during a pre-launch test on the launch pad. The Saturn V, with its crew, never left the ground. The accident grounded the Apollo program for more than 20 months while investigators determined the cause and redesigned the capsule. The Space Shuttle Challenger was lost in January of 1986. 73 seconds after launch, an O-ring seal in one of the solid rocket boosters failed in the cold temperature that morning, leading to a catastrophic structural failure. 7 crew members were gone. Space Shuttle Columbia was lost in February of 2003, disintegrating over Texas and Louisiana during atmospheric re-entry, after foam insulation damage from launch had compromised the thermal protection on the leading edge of the left wing. 7 more crew members were gone. Space does not forgive design oversights, manufacturing flaws, procedural shortcuts, or maintenance failures. The transition from visiting the Moon to living on it would involve incidents and accidents. Equipment failures that, on Earth, would be inconveniences, but in a lunar habitat could be emergencies. Suit failures during EVAs. Life support system malfunctions. Medical emergencies that push the limits of the available care. Perhaps fatalities. Planning for these moments, building in redundancy at every critical point, designing habitats with emergency protocols and fallback systems, creating procedures for every failure mode that can be anticipated, and training until those procedures are instinctive is part of the work. But planning and training don't eliminate risk. They reduce it and manage it and prepare the people facing it. The risk remains. And people will choose to go anyway, because that's what they do. The moon is not a gentle destination. It is not a second Earth waiting to be settled. It is not a world that will cooperate with human presence or meet anyone halfway. It is a 4.5 billion-year-old body that has never had an atmosphere worth speaking of, never had liquid water on its surface for any significant period of time, never had life, never had weather, never had anything to moderate the extremes that space delivers. Every system that makes Earth livable, the atmospheric pressure that keeps your blood in solution, the magnetic shield that deflects the worst of the cosmic radiation, the thermal regulation of oceans and weather, the biological cycling of nutrients through soil, the water cycle that delivers fresh water across the land, the bacterial communities in the soil that make it capable of growing food, none of it is there. Every single day on the moon requires life support systems to function. Not to function elegantly. Not to function comfortably. Just to function. The moment any critical system fails, without a working backup, people could be in danger. And the moon will not wait while you figure out what went wrong. There's a tendency, in the popular imagination of space colonization, to focus on the triumph. The first humans back on the surface. The habitats glowing against a black sky. The scientists making discoveries that change how we understand the solar system. The image of Earth hanging overhead. Those things would be real. But behind every moment of that triumph would be an infrastructure of continuous, demanding, unforgiving work. Life support filters replaced before they saturate. Suit seals inspected before they fail. Water systems maintained before a bacterial bloom compromises the supply. Equipment diagnostics run before something breaks at a critical moment. Agricultural systems monitored before a nutrient deficiency stresses the crops. Backup systems tested before they're needed. Dust cleared from optical surfaces before it degrades performance. All of this, every day, without letting up, because there is no taking a day off from life support. The people who chose to live there anyway would be doing so in full awareness of this. They would be accepting the trade. The confinement, the risk, the physical toll, the distance from everyone familiar, the absence of rain and wind and open sky, in exchange for the chance to be part of something that has genuinely never been done before. To live on another world. To look at Earth and see it for what it actually is, from the outside. To work on problems that matter for the future of the species. To know, with genuine certainty, that they are part of the next chapter of human history. That's not nothing. That's quite a lot. But it should be chosen clearly. Not because someone told you it would be like the movies. Not because the images of Earthrise and softly lit habitats and joyful moonwalks suggested something manageable. Because you understood, fully and honestly, what the actual experience would be. The dust that clings to everything and never settles. The cold that swings between searing and absolute on a 29-day cycle. The radiation that passes through walls and accumulates in cells. The gravity that slowly remakes your body into something that belongs there and not here. The confinement that makes you treasure memories of rain. The distance that turns everyone you love into voices in a speaker. The silence of a world that is 4.5 billion years old and has never once, in all that time, heard a human voice until you spoke. That is the moon. Not the picture on the poster. Not the footage from Apollo. The actual, unvarnished, relentless reality. It is extraordinary, and it is nothing like home. And someday, people will go, and they will stay, and they will build something there that will matter, and they will wake up in a habitat buried under regolith, and suit up to go outside into a world without air or warmth or forgiveness. And they will look up at a blue-white disk in the black sky, and they will know that everyone they've ever loved is on that disk. And they will go to work anyway, because that is the kind of human who goes. The next time you look up at that pale disk in the dark sky, let yourself know what is actually waiting there. The dust that never settles, the cold that never relents, the radiation that moves through walls, the silence that has lasted 4.5 billion years, and the fact that none of it, has ever stopped a human being from going somewhere they wanted to go. Good night.